Imagine standing in a vast room where the walls keep moving away from you, faster and faster, no matter how quickly you run toward them. Now, imagine that room is the entire universe, and the walls are galaxies racing apart at speeds that defy our most fundamental understanding of physics. In the 1920s, when Edwin Hubble first discovered that the universe was expanding, astronomers assumed this expansion would eventually slow down under the weight of gravity, like a ball thrown into the air must eventually fall back to Earth. But in 1998, two independent teams of scientists made a discovery so shocking that it won them the Nobel Prize and shattered every assumption we had about the cosmos. The universe wasn't just expanding, it was accelerating. Something invisible, something we've never detected directly, is pushing the very fabric of space apart with ever-increasing force. We call it dark energy, and it makes up nearly 70% of everything that exists. Yet we have no idea what it is, where it comes from, or why it's tearing the universe apart. Even more troubling, recent measurements suggest the expansion might be happening at different rates in different directions, violating one of the core principles of cosmology. The universe is bigger than it should be, expanding faster than our theories predict, and scientists are genuinely worried about what this means for the future of physics itself. The Hubble tension, when measurements don't agree. In the world of cosmology, few problems have caused as much frustration and excitement as the Hubble tension. At its core lies a simple question: how fast is the universe expanding? The answer should be straightforward: a single number called the Hubble constant, measured in kilometers per second per megaparsec. But when scientists measure this value using different methods, they get different answers, and the gap between these measurements is wide enough that it cannot be explained by experimental error. Something is fundamentally wrong with our understanding of the universe. The first method involves looking at the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation was released about 380,000 years after the universe began, when it cooled enough for atoms to form and light to travel freely. The European Space Agency's Planck satellite mapped this radiation in exquisite detail, measuring tiny temperature fluctuations across the sky. These fluctuations reveal the density of matter and energy in the early universe, and from them, cosmologists can calculate how fast the universe should be expanding today. Using this method, they arrive at a Hubble constant of about 67 kilometers per second per megaparsec. The second method uses a cosmic distance ladder, built from observations of nearby stars and supernovae. Astronomers start by measuring the distances to variable stars called Cepheids, whose brightness pulses at rates that reveal their true luminosity. By comparing how bright these stars appear versus how bright they actually are, scientists calculate their distance. They then use these Cepheids to calibrate distances to Type Ia supernovae stellar explosions that shine with predictable brightness. By measuring how fast these supernovae are moving away from us, and combining that with their distances, astronomers can calculate the expansion rate. Using this method, led by Adam Rees and his team, they get a Hubble constant of about 73 kilometers per second per megaparsec. The discrepancy between 67 and 73 might seem small, but in cosmology it represents a crisis. These are precise measurements, refined over decades by the world's best instruments. The error bars, the range of uncertainty, don't overlap. One measurement says the universe is expanding at one rate, the other says something completely different. Both can't be right, yet both teams have checked their work exhaustively and found no mistakes. This tension has profound implications. If the cosmic microwave background measurement is correct, then something is wrong with our understanding of how stars and supernovae work, the very tools we use to measure cosmic distances. If the distance ladder measurement is correct, then our model of the early universe is incomplete. Either way, the standard model of cosmology, which has successfully explained countless observations, appears to be missing something crucial. Several exotic explanations have been proposed. Some scientists suggest there might be a new type of particle or field that affected the early universe in ways we haven't accounted for. Others propose that dark energy, the mysterious force driving cosmic acceleration, might be changing over time rather than remaining constant. Still others wonder whether Einstein's theory of gravity itself needs modification on cosmic scales. There's even speculation that we might live in a local cosmic void, a region of lower density that would make nearby galaxies appear to recede faster than the universal average. Recent observations have only deepened the mystery. The James Webb Space Telescope has confirmed the distance ladder measurements with unprecedented precision, ruling out several possible sources of systematic error. Multiple independent teams using different methods have converged on the higher value of the Hubble constant. Meanwhile, measurements of the cosmic microwave background remain robust, showing no signs of hidden flaws. The tension isn't going away, it's getting stronger. Some researchers now argue that this discrepancy might be our first real glimpse of physics beyond the standard model. Throughout history, unexplained observations have led to revolutionary discoveries. The strange orbit of Mercury led Einstein to general relativity. The unexpected spectrum of black-body radiation gave birth to quantum mechanics. Perhaps the Hubble tension is pointing us toward a similar breakthrough, a hint that the universe operates by rules we haven't yet discovered. What makes this particularly exciting and unsettling is that the answer could reshape our understanding of everything from the Big Bang to the ultimate fate of the cosmos. Dark energy, the invisible force tearing space apart. In 1998, two teams of astronomers set out to measure how much the universe's expansion was slowing down. They expected to find that gravity, pulling on all the matter in the cosmos, was gradually putting the brakes on expansion, perhaps enough to eventually halt it entirely or even reverse it into a big crunch. Instead, they discovered something that defied every expectation. The universe's expansion wasn't slowing down at all. It was speeding up. This acceleration had been increasing for the past 6 billion years, as if something was actively pushing space apart with growing strength. The discovery was so unexpected that both teams initially thought they had made a mistake. The measurements came from observations of Type Ia supernovae stellar explosions that occur when white dwarf stars accumulate too much mass from a companion and undergo catastrophic nuclear fusion. These explosions are remarkably consistent in brightness, making them perfect cosmic mile markers. By comparing how bright they appear versus how bright they should be, astronomers can calculate their distance. By measuring their redshift, how much their light has been stretched by cosmic expansion, astronomers can determine how fast they're moving away from us. When researchers plotted distance against velocity for dozens of these supernovae, they expected to see the expansion rate decreasing over time. Instead, they found the opposite pattern. Distant supernovae, whose light was emitted billions of years ago, were receding slower than expected. Recent ones were receding faster. The expansion rate was increasing. The implications were staggering. Some unknown form of energy must be filling space itself, exerting a repulsive force that overpowers gravity on cosmic scales. Scientists called it dark energy. Though the name is somewhat misleading, it's not dark in the sense of blocking light, and it's not energy in any conventional sense. It's more like a property of empty space, a kind of anti-gravity embedded in the vacuum itself. According to Einstein's equations, empty space can have energy, and this energy creates a repulsive gravitational effect. Einstein had actually proposed exactly this concept in 1917, adding a term called the cosmological constant to his equations to keep the universe static, as was believed at the time. When Hubble discovered cosmic expansion in 1929, Einstein famously called the cosmological constant his biggest blunder and removed it. Now, 70 years later, it had returned not to make the universe static, but to explain why it was accelerating. The amount of dark energy required to explain the observations is enormous. Current measurements indicate it makes up approximately 68% of the total energy density of the universe. Dark matter contributes another 27%. Everything else, all the stars, planets, gas, dust, and radiation, we can observe accounts for less than 5%. In other words, the universe is dominated by two completely invisible components we don't understand, and the larger of the two is actively driving everything apart. What exactly is dark energy? The honest answer is that we don't know. The leading explanation is Einstein's cosmological constant, a fundamental property of space that never changes. In this view, empty space has an inherent energy density of about 10 to the power of -9 joules per cubic meter. It sounds tiny, but when multiplied across the vast volume of the universe, it becomes the dominant force in cosmic evolution. This energy doesn't dilute as space expands. Instead, as the universe grows, more space appears, and with it, more dark energy. This creates a feedback loop. Dark energy causes expansion. Expansion creates more space. More space contains more dark energy, which accelerates expansion further. Alternative theories propose that dark energy might not be constant. Some models suggest it could be a dynamic field called quintessence, which slowly evolves over cosmic time. Others propose that dark energy might be a sign that Einstein's theory of gravity breaks down on the largest scales and needs modification. Still others suggest we might need entirely new physics, particles or forces or dimensions we haven't yet conceived of. The range of possibilities reflects our profound ignorance. Observational programs are working to constrain these models. The Dark Energy Survey mapped hundreds of millions of galaxies to trace how cosmic structure has grown over time. The Dark Energy Spectroscopic Instrument is measuring the positions and redshifts of tens of millions of galaxies to create the most detailed three-dimensional map of the universe ever made. The Euclid Space Telescope is examining how dark energy has shaped the distribution of matter over billions of years. The Vera Rubin Observatory will survey the entire visible sky every few nights, tracking how galaxies move and cluster under dark energy's influence. What makes dark energy particularly troubling is that quantum field theory, our best description of particle physics, predicts that empty space should have energy, but the predicted value is about 10 to the power of 120 times larger than what we observe. This is often called the worst prediction in the history of physics. Why the actual value is so much smaller remains one of the deepest mysteries in science. Some researchers invoke the anthropic principle, arguing that only in a universe with this particular value of dark energy could galaxies, stars, and life exist. Others believe there must be some unknown mechanism that cancels out most of the vacuum energy, leaving only the tiny residual we detect, the accelerating expansion and what it means. The discovery that cosmic expansion is accelerating fundamentally changed our picture of the universe's future. Before 1998, cosmologists debated whether the universe would expand forever, gradually slowing under gravity's pull, or eventually collapse back on itself in a big crunch. Dark energy has settled that debate in the most dramatic way possible. Not only will the universe expand forever, the expansion will continue to accelerate, ultimately determining the fate of every galaxy, star, and atom in existence. To understand what this means, we need to think about how cosmic expansion affects different scales. On small scales inside galaxies and galaxy clusters, gravity dominates completely. Dark energy's repulsive effect is too weak to overcome the gravitational binding of these structures. The Milky Way won't be torn apart, nor will our local group of galaxies. These systems are gravitationally bound and will continue to evolve according to gravity's rules. The same applies to larger structures like galaxy clusters and even superclusters, as long as they're already collapsed into coherent systems. But on larger scales, beyond gravitationally bound structures, dark energy wins. Galaxies that aren't already connected by gravity are being pushed apart at an accelerating rate. As space expands between them, the recession velocity increases. Eventually, galaxies far enough away are receding faster than the speed of light, not because they're moving through space that fast, but because the space between us and them is expanding faster than light can cross it. This doesn't violate relativity because nothing is actually moving faster than light through space. Rather, space itself is expanding. The implications become stark when we project this expansion into the future. Currently, we can observe galaxies out to about 46 billion light-years away. The edge of our observable universe, defined by the distance light has been able to travel since the Big Bang. But this observable horizon isn't fixed. As time passes and expansion accelerates, distant galaxies will cross what's called the cosmic event horizon, the boundary beyond which they can never send us signals again. Objects beyond this horizon are receding so fast that even light they emit toward us gets carried away by expansion and never reaches us. About 100 billion years from now, the observable universe will look very different from a future vantage point. The Milky Way will have merged with Andromeda and possibly other local group members, forming a giant elliptical galaxy. But beyond this merged system, the sky will be dark. Every galaxy currently visible will have crossed the cosmic event horizon and disappeared from view. The cosmic microwave background radiation, the afterglow of the Big Bang, will have redshifted to such long wavelengths that it becomes undetectable. Future astronomers living in this era will see only their own galaxy surrounded by empty blackness. They'll have no way to discover that the universe is expanding, no evidence of the Big Bang, and no reason to believe other galaxies ever existed. The cosmological constant problem. Physicists face an embarrassing problem when it comes to dark energy. Quantum field theory, our most successful description of fundamental physics, makes a prediction about the energy of empty space that's wrong by a factor of 10 to the power of 120. This isn't just a minor discrepancy or a rounding error, it's the largest mismatch between theory and observation in the history of science. Understanding why this prediction fails so spectacularly is considered one of the deepest unsolved problems in theoretical physics. The problem arises from a fundamental aspect of quantum mechanics. According to quantum field theory, empty space isn't actually empty. It's filled with quantum fields that permeate all of space, and these fields constantly fluctuate even in their lowest energy state. These vacuum fluctuations create pairs of virtual particles that pop into existence and annihilate each other in tiny fractions of a second. We know these fluctuations are real because they produce measurable effects like the Casimir force, where two metal plates placed very close together in a vacuum experience an attractive force caused by the difference in vacuum energy between the plates and the surrounding space. Each quantum field contributes to the total energy of the vacuum. When physicists calculate the sum of all these contributions, they get an absurdly large number. If this calculation were correct, the vacuum energy density would be about 10 to the power of 113 joules per cubic meter. Such an enormous energy density would cause the universe to expand so violently that atoms couldn't form, let alone stars and galaxies. Yet we observe a vacuum energy density of roughly 10 to the power of negative 9 joules per cubic meter tiny, but not zero. Something must be cancelling out almost all of the predicted vacuum energy, leaving only the minuscule residual we detect as dark energy. Various solutions have been proposed, none entirely satisfactory. One approach invokes supersymmetry, a theoretical framework that predicts every known particle has a heavier partner particle. In supersymmetric theories, the contributions to vacuum energy from particles and their superpartners would exactly cancel out, yielding zero cosmological constant. But supersymmetry would only solve the problem if it were an exact symmetry. Since we don't observe superpartner particles at the energies we've probed so far, supersymmetry must be broken, and broken supersymmetry generically predicts a large cosmological constant again back to square one. Another approach suggests that the small value of dark energy might be explained by the anthropic principle. In this view, there might be a vast number of universes, a multiverse with different values of the cosmological constant. Most of these universes would be inhospitable to life. If dark energy were much larger, galaxies wouldn't form, and if it were much smaller or negative, the universe might recollapse before stars could form. We necessarily find ourselves in one of the rare universes where the cosmological constant is small enough to allow structure, formation, and life. While this argument might be logically sound, many physicists find it unsatisfying because it doesn't predict the value of dark energy or explain the mechanism that generates different universes. A more radical possibility is that we're thinking about dark energy the wrong way. Perhaps it's not vacuum energy at all, but something else entirely, a new field, a modification to gravity, or even a sign that space-time has more dimensions than we realize. String theory, for instance, suggests there might be 6 or 7 extra spatial dimensions curled up at scales too small to detect. The geometry of these extra dimensions could affect the effective cosmological constant in our observable 4-dimensional universe. However, string theory has its own version of the cosmological constant problem. It appears to predict an enormous number of possible vacuum states, each with different physics, making concrete predictions difficult. Is dark energy changing over time? One of the most important questions about dark energy is whether it remains constant or changes as the universe evolves. If dark energy is Einstein's cosmological constant, then by definition it never changes. It's a fixed property of space itself, the same everywhere and at all times. But if dark energy is something else, some kind of dynamic field, then its strength could vary across cosmic history. Determining which scenario is correct has profound implications for the universe's fate. Cosmologists have devised a way to test this using a parameter called the equation of state, denoted by the symbol W. This parameter describes the relationship between dark energy's pressure and its energy density. For a true cosmological constant, W equals exactly -1. If dark energy is something else, a field called quintessence, for example, then we could have a different value, and that value might change over time. Measuring W and tracking how it evolves tells us what kind of dark energy we're dealing with. Several major observational programs have attempted to measure W with increasing precision. The Supernova Cosmology Project and the High-Z Supernova Search Team, which discovered cosmic acceleration in 1998, provided the first rough constraints. Later surveys like the Dark Energy Survey and the Sloan Digital Sky Survey refined these measurements by mapping millions of galaxies and tracking how cosmic structure grew over billions of years. The Planck satellite measured fluctuations in the cosmic microwave background to constrain W from the opposite direction, looking at the early universe rather than the late universe. Results so far are consistent with W being equal to -1 within the uncertainties of the measurements, supporting the cosmological constant interpretation, but the error bars are still large enough to allow for some variation. Recent analyses combining multiple datasets suggest W is somewhere between -1.03 and -0.96, with the best fit value sitting very close to -1. This consistency is both reassuring and frustrating. Reassuring because the simplest model still works, frustrating because it doesn't point toward new physics. If future measurements definitively show that W is not exactly a -1, or that it changes over time, the implications would be revolutionary. A value of W slightly less than -1, say -1.1, would imply phantom energy, a form of dark energy even more repulsive than the cosmological constant. Phantom energy would cause the expansion to accelerate so rapidly that it would eventually overcome all forces, even gravity and electromagnetism, tearing apart galaxies, stars, planets, and eventually atoms themselves in an event called the Big Rip. On the other hand, if W is slightly greater than -1, dark energy might be weakening over time, potentially allowing gravity to regain control billions of years from now. The quest to measure W more precisely drives much of modern observational cosmology. The Dark Energy Spectroscopic Instrument is measuring redshifts for tens of millions of galaxies to map how dark energy has affected cosmic expansion over the past 11 billion years. The European Space Agency's Euclid mission is mapping billions of galaxies to trace how dark energy has shaped the growth of structure. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct massive surveys of supernovae and galaxies to constrain W to within a few percent. These missions face daunting technical challenges. Measuring W accurately requires understanding how galaxies were distributed billions of years ago and comparing that to their distribution today. It requires precise distance measurements to objects billions of light years away. It requires accounting for countless sources of systematic error, from dust obscuring distant galaxies to biases in how telescopes select which objects to observe. Yet despite these challenges, the potential payoff is enormous. If we discover that W is not a -1, we'll know that the cosmological constant is wrong and that the universe is driven by something far stranger: modified gravity theories. As the Hubble tension persists and dark energy remains mysterious, some physicists have begun questioning whether gravity itself behaves differently on cosmic scales than Einstein's general relativity predicts. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy at all, instead proposing that the laws of gravity change when applied to the entire universe. While general relativity has passed every experimental test in the solar system and in binary pulsar systems, it has never been directly tested on scales of billions of light years, precisely the scales where dark energy dominates. The motivation for modifying gravity comes from a simple observation. We've never detected dark energy directly. We infer its existence only from its gravitational effects on cosmic expansion and structure formation. But what if those effects don't come from a mysterious new form of energy? What if they arise because gravity works differently than we think on cosmological scales? This would mean we've been interpreting the data incorrectly, attributing to dark energy what's actually a signature of modified gravitational physics. One of the earliest and simplest modifications is called FR gravity. In general relativity, the curvature of spacetime, denoted R, is directly related to the distribution of matter and energy. In FR theories, this relationship is modified by replacing R with some function FR. Depending on the choice of function, this can produce accelerated expansion without requiring dark energy. The challenge is choosing a function that matches observations of cosmic expansion while still agreeing with solar system tests of gravity, which constrain modifications very tightly. Another approach is called massive gravity, which gives the graviton, the hypothetical particle that mediates gravitational force, a tiny but non-zero mass. In ordinary general relativity, gravitons are massless, allowing gravity to act over infinite distances. If gravitons have mass, gravity's strength would decrease slightly at very large distances, potentially weakening its pull on cosmic scales and allowing expansion to accelerate. Massive gravity theories face significant theoretical challenges, including instabilities that can make them inconsistent, but recent formulations have found ways around some of these problems. Scalar tensor theories represent another class of modifications. These theories introduce an additional field, a scalar field that couples to gravity and affects how matter curves spacetime. The most famous example is Brans-Dicke theory, proposed in the 1960s, which includes a scalar field that determines the effective strength of gravity. Modern versions of scalar tensor theories can produce cosmic acceleration while remaining consistent with solar system observations. Some of these theories are nearly indistinguishable from dark energy models observationally, making them difficult to rule out. Perhaps the most radical modification is emergent gravity, which proposes that gravity isn't a fundamental force at all, but rather emerges from more fundamental physics, much like thermodynamics emerges from the statistical behavior of atoms. In Eric Verlinde's controversial theory, gravity arises from the entropy of information stored on the boundary of space. This approach naturally produces a force that looks like dark energy on large scales while reducing to standard gravity on smaller scales. However, emergent gravity theories are still highly speculative and face significant challenges in matching detailed observations. Testing modified gravity theories requires observations that can distinguish them from dark energy models. One promising approach uses weak gravitational lensing, the subtle distortion of distant galaxy images caused by intervening mass. In general relativity with dark energy, the growth of cosmic structure and the bending of light are linked in a specific way. Modified gravity theories generally predict different relationships between structure growth and lensing, offering a way to test them. The Dark Energy Survey, the Kilo Degree Survey, and upcoming missions like Euclid are collecting precisely the data needed for these tests. The Cosmic Microwave Background Anomalies. The cosmic microwave background radiation is the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos cooled enough for atoms to form and photons to travel freely. This faint glow, now stretched by cosmic expansion to microwave wavelengths, fills all of space and carries a detailed snapshot of the infant universe. For decades, measurements of the CMB have confirmed the standard model of cosmology with remarkable precision, but hidden within this ancient light are subtle anomalies that hint our understanding might be incomplete. The European Space Agency's Planck satellite, which operated from 2009 to 2013, mapped the CMB with unprecedented accuracy. The resulting all-sky map shows tiny temperature variations, typically just tens of millionths of a degree across different directions in the sky. These fluctuations reflect density variations in the early universe that eventually grew into galaxies and clusters. Planck's measurements allowed cosmologists to determine the universe's age, composition, and expansion rate with extraordinary precision. Yet within this otherwise perfect agreement, several puzzling features emerged. The first anomaly involves the largest angular scales, the biggest patterns visible in the CMB. According to the standard cosmological model, the temperature fluctuations on these scales should follow a specific statistical distribution. But observations show that the largest fluctuations are significantly weaker than predicted. This deficit of power on large scales, first noticed by the earlier WMAP satellite and confirmed by Planck, has no obvious explanation within the standard model. It could be a statistical fluke. Large-scale fluctuations are rare, so we have limited data, but the discrepancy is large enough to raise questions. A related anomaly is the cold spot, a particularly large region of the CMB that's colder than expected. Located in the direction of the constellation Eridanus, this region spans about 10 degrees across the sky, roughly 20 times the diameter of the full moon. While cold regions are expected in a random distribution of temperature fluctuations, the cold spot is colder and larger than statistical predictions suggest it should be. Some astronomers have proposed it might be caused by a supervoid, an unusually large empty region in space that light passes through on its way to us, losing energy in the process. Others speculate it could be evidence of a collision between our universe and another in a multiverse, though this interpretation is highly controversial. Another puzzling feature is the hemispherical asymmetry. The standard cosmological model predicts that temperature fluctuations in the CMB should be statistically identical in all directions. The universe should look the same no matter which way we look. But observations reveal a subtle but persistent difference between fluctuations in one hemisphere of the sky versus the opposite hemisphere. One side shows slightly larger temperature variations than the other. This asymmetry shouldn't exist if the universe is homogeneous and isotropic as the standard model assumes. The CMB also exhibits odd alignments between fluctuations at different scales, sometimes called the axis of evil. Certain large-scale patterns in the temperature map appear to align with each other, and with the ecliptic plane of the solar system, the plane in which Earth orbits the Sunday. This alignment is deeply strange because there should be no connection whatsoever between structures in the early universe and the orientation of our solar system, which formed billions of years later. Most cosmologists believe this is probably a coincidence, but it's an unsettling one that has resisted explanation. Some researchers have proposed exotic explanations for these anomalies. Perhaps the universe isn't perfectly isotropic, and there's a preferred direction in space related to cosmic inflation or the geometry of higher dimensions. Perhaps we live near the edge of a region with different properties from the rest of the universe. Perhaps quantum fluctuations during inflation created patterns that violate the assumptions of the standard model. Or perhaps, and this is the most conservative view, these anomalies are simply statistical flukes that happen to occur in our particular observable patch of the universe. Cosmic voids and the large-scale structure. When astronomers map the distribution of galaxies across billions of light-years, they don't see a uniform spread of matter. Instead, galaxies are arranged in a vast cosmic web, an intricate network of filaments, walls and nodes surrounding enormous empty regions called cosmic voids. These voids are the largest structures in the universe, some spanning hundreds of millions of light-years across. Understanding their properties and distribution is crucial for testing cosmological models and measuring cosmic expansion. Cosmic voids form naturally in an expanding universe. In the early universe, matter was distributed almost uniformly, with only tiny density variations, the same fluctuations visible in the cosmic microwave background. As the universe evolved, gravity amplified these variations. Regions slightly denser than average attracted more matter, growing into filaments and clusters. Regions slightly less dense than average lost matter to their denser neighbours, becoming increasingly empty. Over billions of years, this process created the cosmic web we observe today, with most galaxies concentrated along filaments and dense nodes, while vast voids contain very few galaxies. The properties of voids provide powerful tests of cosmological models. In a universe dominated by dark energy, voids should expand faster than the universe's average expansion rate. This happens because voids contain less matter and therefore experience weaker gravitational attraction trying to slow expansion. Meanwhile, the repulsive effect of dark energy acts everywhere equally. The combination means voids grow and empty out more rapidly than denser regions. By measuring how fast voids expand and how their sizes change over cosmic time, astronomers can constrain the properties of dark energy independently of other methods. One of the largest voids known is the Boyter's void, discovered in 1981, spanning approximately 330 million light-years across. This region contains far fewer galaxies than expected. While not completely empty, it contains about 60 known galaxies. Its density is roughly 1/10 of the cosmic average. Astronomers have since discovered even larger voids, including supervoids that can reach 500 million light-years or more in diameter. These structures are so enormous that light takes hundreds of millions of years to cross them. The existence of such large voids creates a subtle but measurable effect on the cosmic microwave background called the integrated Sachs-Wolf effect. When CMB photons pass through a void, they fall into its gravitational potential well, gaining energy. As they climb back out the other side, they lose energy. In a static universe, these effects would cancel perfectly. But because voids expand and become less dense over time, their gravitational potential changes while photons are crossing them. This creates a net change in the photon's energy. which appears as a slight temperature difference in the CMB. Measuring this effect allows astronomers to map voids using both galaxy surveys and CMB observations simultaneously. Recent surveys have catalogued thousands of voids across the observable universe. Projects like the Sloan Digital Sky Survey and the Dark Energy Survey have mapped how voids are distributed and how their properties correlate with the large-scale structure. These measurements reveal that void sizes follow a predictable distribution, with most voids being relatively modest in size and only a few reaching supervoid scales. The distribution depends on the properties of dark energy and dark matter, offering another way to constrain these mysterious components. Baryon acoustic oscillations, sound waves from the early universe. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma where matter and radiation were tightly coupled. Sound waves, pressure waves propagating through this primordial soup travelled outward from regions of higher density, creating a characteristic scale imprinted on the distribution of matter. Today, billions of years later, this relic scale still appears as a subtle pattern in how galaxies cluster. Measuring this pattern, called baryon acoustic oscillations, provides one of the most powerful tools for studying cosmic expansion and dark energy. The physics behind baryon acoustic oscillations is straightforward. In the early universe, photons constantly scattered off electrons, creating pressure that resisted gravitational collapse. This pressure allowed sound waves to propagate through the plasma at about 57% the speed of light. These waves travelled outward from initial density peaks, carrying matter with them. When the universe was 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Photons decoupled from matter and streamed freely through space, creating the cosmic microwave background. Without photon pressure, the sound waves stopped propagating, freezing a characteristic scale into the distribution of matter roughly 500 million light-years in today's universe. This scale manifests as a subtle excess in the probability of finding pairs of galaxies separated by about 500 million light-years compared to slightly smaller or larger separations. It's not that galaxies form a regular grid at this spacing, the effect is statistical, appearing only when averaging over millions of galaxies across vast volumes of space. But with modern galaxy surveys that catalogue millions of objects, astronomers can detect this subtle signal and use it as a standard ruler to measure cosmic distances. The beauty of baryon acoustic oscillations as a cosmological probe comes from their simplicity and robustness. The scale is set by basic physics in the early universe, the sound speed in the plasma, and the time available for waves to propagate before recombination. These can be calculated precisely from measurements of the cosmic microwave background, giving us a known physical length. By measuring how large this scale appears in the angular distribution and redshift distribution of galaxies at different cosmic epochs, astronomers can determine how the universe has expanded over time. Major observational programs have exploited this technique. The Baryon Oscillation Spectroscopic Survey, BOSS, part of the Sloan Digital Sky Survey, measured positions and redshifts for 1.5 million galaxies, mapping cosmic structure over a volume of billions of cubic light-years. The Dark Energy Spectroscopic Instrument is extending these measurements to 35 million galaxies, probing earlier cosmic epochs and achieving unprecedented precision. The Euclid Space Telescope will map billions of galaxies, measuring baryon acoustic oscillations across the entire history of cosmic expansion from the present back to when the universe was less than 1/4 its current age. Results from these surveys consistently confirm cosmic acceleration, but also contribute to the Hubble tension. Measurements of baryon acoustic oscillations favour the lower value of the Hubble constant derived from the cosmic microwave background, around 67 kilometers per second, per megaparsec, in conflict with local measurements using Cepheid variables and supernovae. This agreement between two completely independent methods based on the early universe strengthens the case that something might be wrong with our understanding of how stars work or how we measure cosmic distances locally. The local void hypothesis. One proposed resolution to the Hubble tension invokes our cosmic neighbourhood. What if the Milky Way happens to sit inside or near a region of lower than average density, a local void? If so, the expansion rate we measure from nearby galaxies might not represent the universe's true average expansion rate. This is called the local void hypothesis, and while it remains controversial, it offers a way to reconcile conflicting measurements without abandoning established physics. The logic behind this idea is that density affects expansion. In denser regions, gravity is stronger, pulling more effectively against cosmic expansion, and causing the local expansion rate to be slower than the cosmic average. In less dense regions, void's gravity is weaker, allowing expansion to proceed faster than average. If we happen to live in a region that's slightly underdense, we would measure a faster local expansion rate, even though the universe's overall average expansion matches the slower rate inferred from the cosmic microwave background. For this hypothesis to work, the underdensity would need to be significant and extend out to distances of hundreds of millions of light-years, far enough to encompass all the galaxies we use for local distance measurements, but not so large that it conflicts. With observations of the cosmic microwave background, which samples the universe on vastly larger scales, several studies have looked for evidence of such a void by mapping the distribution of galaxies around us. Some observations do suggest we might be in a modest underdensity. The KBC void, named after its discoverers, is a proposed underdense region roughly 2 billion light-years across, centered approximately on our location. Surveys indicate that the average density of galaxies within this region is about 20% lower than the cosmic mean. If this underdensity is real and extends deep enough, it could potentially explain a portion of the Hubble tension by making nearby supernovae appear to recede faster than they would in an average environment. However, the local void hypothesis faces significant challenges. First, observations of the cosmic microwave background place strict limits on how underdense a large region around us can be. Large voids create distinctive patterns in the CMB through the integrated Sachs-Wolf effect, and measurements constrain such features tightly. For a void to explain the full Hubble tension without violating CMB observations, it would need to have a very specific profile, moderate underdensity, extending over a large volume, and it's unclear whether such configurations arise naturally in cosmological simulations. Second, independent measurements using baryon acoustic oscillations and other methods that don't rely on the local distance ladder also favour the lower value of the Hubble constant. These measurements probe much larger volumes, averaging over many voids and overdense regions, so they shouldn't be significantly affected by local underdensity. Their agreement with the cosmic microwave background suggests the tension isn't purely a local environmental effect. Third, recent high-precision measurements from the James Webb Space Telescope have confirmed the distance ladder results with independent methods, reducing the likelihood that systematic errors in distance measurements are responsible for the tension. JWST's infrared capabilities allow it to observe Cepheid variables with less interference from dust and to check distance measurements using alternative standard candles. So far, these checks have validated the higher expansion rate, making the local void explanation less likely to be the full answer. The role of gravitational waves in measuring expansion. Gravitational waves, ripples in spacetime, produced by accelerating massive objects, have opened an entirely new way to measure cosmic expansion. Unlike light-based methods that rely on standard candles or standard rulers, gravitational wave observations can provide direct distance measurements independent of the cosmic distance ladder. This makes them potentially powerful tools for resolving the Hubble tension and understanding dark energy. The key lies in what astronomers call standard sirens, an analogy to standard candles. When two neutron stars or black holes spiral together and merge, they emit gravitational waves whose amplitude depends on the distance to the source. Detectors like LIGO and Virgo measure this amplitude, directly determining how far away the merger occurred. If the merger can also be observed electromagnetically if it produces light, astronomers can measure its redshift and thus its recession velocity. Combining distance and velocity gives an independent measurement of the Hubble constant, requiring no distance ladder and no assumptions about how stars evolve. The first such measurement came in 2017 with the detection of gravitational waves from a neutron star merger, designated GW170817. This event was revolutionary because it was observed both in gravitational waves and across the electromagnetic spectrum. The Fermi and Integral satellites detected gamma rays from the merger seconds after the gravitational wave signal arrived at Earth. Within hours, dozens of telescopes identified the optical counterpart, a kilonova, a radioactive glow from heavy elements synthesized in the merger debris. Detailed observations allowed astronomers to identify the host galaxy, NGC 4993, and measure its redshift. By combining the gravitational wave distance with the redshift, researchers calculated a Hubble constant of approximately 70 kilometers per second per megaparsec, with large uncertainties due to this being a single event. This value sits tantalizingly between the two conflicting measurements from the cosmic microwave background and the distance ladder, offering no clear resolution but demonstrating the method's potential. The challenge with standard sirens is that most gravitational wave events detected so far have been mergers of black holes, which produce no light and therefore no redshift measurement. Only neutron star mergers reliably produce electromagnetic counterparts bright enough to identify the host galaxy. These events are rarer than black hole mergers and occur at greater average distances where electromagnetic signals are fainter and harder to detect. Out of nearly 100 gravitational wave events detected through 2023, only a handful have confirmed electromagnetic counterparts. Future gravitational wave detectors promise to change this situation dramatically. The planned Einstein telescope in Europe and Cosmic Explorer in the United States will be 10 times more sensitive than current detectors, allowing them to observe neutron star mergers throughout most of the observable universe. With this increased sensitivity, astronomers expect to detect hundreds of standard sirens per year, enabling precise measurements of cosmic expansion at multiple redshifts. This will not only determine the Hubble constant with unprecedented accuracy, but also trace how dark energy has affected expansion over billions of years. Space-based gravitational wave detectors like LISA, Laser Interferometer Space Antenna, planned for launch in the 2030s, will access different frequency ranges and detect different types of sources. LISA will observe supermassive black hole mergers in distant galaxies, providing standard siren measurements across cosmic history back to the early universe. These observations could reveal whether dark energy's strength has changed over time, directly testing whether it's truly a cosmological constant or something more dynamic. Cosmic expansion in different directions. One of the fundamental assumptions of modern cosmology is that the universe looks essentially the same in all directions that it's isotropic. This assumption underpins the standard cosmological model and simplifies calculations enormously. But what if it's wrong? What if cosmic expansion proceeds at different rates in different directions? Recent observations have raised precisely this unsettling possibility, suggesting the universe might be more complex than our models assume. The idea that expansion might be anisotropic isn't entirely new. As far back as the 1960s, cosmologists explored models where the universe expanded at different rates along different axes, creating what's called a Bianchi cosmology. These models fell out of favor because observations of the cosmic microwave background showed it to be extremely uniform across the sky, indicating that if any anisotropy exists, it must be very small. But modern precision measurements have revealed subtle anomalies that could hint at directionality in cosmic expansion. One piece of evidence comes from studying the distribution of galaxy velocities. When researchers map how galaxies move in different regions of the sky, accounting for both cosmic expansion and local peculiar velocities, they sometimes find patterns inconsistent with perfectly isotropic expansion. Some analyses suggest galaxies in certain directions might be receding slightly faster than those in opposite directions, even after accounting for local gravitational effects. These differences are small, a few percent at most, but persistent across multiple independent datasets. Another hint comes from measurements of the kinematic dipole, our motion relative to the cosmic microwave background. Earth, the Sun, and the Milky Way are all moving through space, and this motion creates a Doppler shift in the CMB. It appears slightly warmer in the direction we're moving toward, and slightly cooler in the opposite direction. This dipole has been measured precisely and tells us we're moving at about 370 kilometers per second relative to the CMB rest frame. The question is, what's causing this motion? Standard cosmology explains the dipole through gravitational attraction. Massive structures like the Shapley supercluster pull on our local group, accelerating us through space. But when researchers map the distribution of nearby galaxies and calculate the expected gravitational pull, the direction and magnitude sometimes don't quite match the observed dipole. There's a residual velocity component that's hard to explain with local mass distributions alone. Some studies suggest this might indicate that the cosmic rest frame itself, the frame in which the CMB is isotropic, varies with direction, implying anisotropic expansion. Further evidence comes from measurements of the Hubble constant in different parts of the sky. When researchers divide the sky into different regions and measure the expansion rate using supernovae or other distance indicators in each region separately, they sometimes find systematic variations. The expansion rate in one direction might be a few percent higher than in another. Most of these variations are probably due to local mass concentrations affecting velocities, the Shapley supercluster pulling galaxies one way, a large void pushing them another. But some researchers argue the patterns are too large or too systematic to be explained by local structure alone. The most controversial suggestion is that these anomalies might indicate we're living in a Hubble bubble, a region where the expansion rate differs from the cosmic average, with the difference varying depending on direction within the bubble. Such a configuration would arise naturally if our observable universe sits inside or near a large-scale cosmic structure whose properties vary across the sky. This would mean the Hubble constant we measure locally doesn't represent the universe's true expansion rate, potentially explaining the Hubble tension, the phantom energy scenario. While most evidence points toward dark energy being Einstein's cosmological constant, a fixed property of space that never changes, some theoretical possibilities are far more dramatic. One of the most extreme scenarios involves phantom energy, a hypothetical form of dark energy that becomes stronger over time. If phantom energy exists, it doesn't just drive cosmic expansion, it accelerates that expansion at an ever-increasing rate, ultimately tearing apart every structure in the universe, from galaxy clusters down to atoms, in an event called the Big Rip. The distinction between phantom energy and a cosmological constant comes down to the equation of state parameter W. For a cosmological constant, W equals exactly -1. For phantom energy, W is less than -1, typically values like -1.1 or -1.2. This seemingly small difference has catastrophic consequences over cosmic timescales. While dark energy with W equals -1 drives acceleration, phantom energy drives superacceleration. The expansion rate doesn't just increase, the rate of increase itself increases, creating runaway growth. Current observations place a close to -1, but with error bars that still allow for phantom energy within the uncertainties. Several independent analyses combining supernovae, baryon acoustic oscillations, and cosmic microwave background data find best fit values of W slightly below -1, though not conclusively so. If future measurements confirm W is significantly less than -1, we would know phantom energy is real, and the universe faces an extraordinary fate. In a phantom energy universe, the timeline to destruction depends on exactly how far below -1 W falls. For W around -1.5, the Big Rip would occur roughly 22 billion years from now. The sequence of events follows a grim progression. First, about 200 million years before the end, galaxy clusters become unbound as phantom energy's repulsive effect overcomes their gravity. Individual galaxies drift apart, isolated in empty space. Then, about 60 million years before the end, galaxies themselves disintegrate. The Milky Way would tear apart, its spiral arms dissolving as stars scatter into the void. 3 months before the end, planetary systems become unbound. Earth would drift away from the Sun, along with all other planets, wandering alone through the darkness. In the final weeks, the expanding space becomes strong enough to overcome chemical bonds. Planets disintegrate into clouds of atoms. In the last moments, even atoms themselves are torn apart as space expands faster than electromagnetic forces can hold nuclei and electrons together. The universe ends not in heat or cold, but in complete fragmentation, with every particle separated from every other, unable to interact, in a state of maximal entropy and isolation. Phantom energy poses profound theoretical challenges. In quantum field theory, phantom fields generally violate energy conditions, mathematical requirements that most sensible forms of matter and energy obey. Systems with phantom energy can develop instabilities, allowing vacuum decay or the creation of infinite amounts of energy from nothing. These problems make many physicists skeptical that phantom energy can exist as a fundamental field. However, some theorists have constructed models where phantom-like behavior emerges from more conventional physics through complex interactions between multiple fields, the multiverse and eternal inflation. The discovery of dark energy and cosmic acceleration has revived one of the most ambitious and controversial ideas in theoretical physics, the multiverse. According to this concept, our observable universe, everything we can see out to 46 billion light-years in every direction, is just one small region within a vastly larger cosmos containing countless other regions with different physical properties. Dark energy plays a central role in multiverse theories by driving eternal inflation, a process that continually creates new universe regions forever. The story begins with cosmic inflation, the idea that the universe underwent a brief period of exponential expansion in its first fraction of a second. Proposed in the 1980s to explain why the universe is so smooth and flat, inflation solves several cosmological puzzles. The original inflation models predicted that this exponential growth would eventually end everywhere as the inflation field decayed, leaving behind a uniform universe filled with matter and radiation, the hot Big Bang state from which our observable universe evolved. But in the 1980s, physicists realized that quantum fluctuations could prevent inflation from ending everywhere simultaneously. In most of space, the inflation field would decay, creating pocket universes like ours. But in some regions, quantum fluctuations would drive the field to higher energy states, causing those regions to inflate even faster. These inflating regions would grow enormously, and within them, quantum fluctuations would again create both decaying and inflating patches. This process continues forever, hence eternal inflation, producing an infinite number of pocket universes embedded in an eternally inflating background. Each pocket universe could have different properties. The laws of physics as we know them arise from the configuration of quantum fields and the geometry of extra dimensions in string theory. During inflation, these configurations could freeze into different patterns in different pockets, giving each region its own effective physical laws. Some pockets might have stronger electromagnetic forces, others weaker gravity, still others different numbers of particle types or spatial dimensions. Most configurations would be inhospitable to life. Stars wouldn't form, atoms wouldn't be stable, chemistry wouldn't work. But somewhere in this vast multiverse, regions with properties like ours would exist. Dark energy fits naturally into this picture. In string theory, the vacuum energy, the cosmological constant, depends on the configuration of fields and dimensions. Different configurations produce different vacuum energies, ranging from large positive values to large negative values. Most would produce either runaway expansion or immediate collapse. Only a tiny subset of configurations yield small positive cosmological constants, like the one we observe, just large enough to eventually dominate and cause acceleration, but small enough to allow galaxies to form first. We necessarily find ourselves in one of these rare pockets because only such regions can support observers. This is the anthropic principle applied to dark energy. We observe the cosmological constant we do, not because it's somehow special or predicted by fundamental physics, but because if it was significantly different, we wouldn't exist to observe it. While this reasoning might seem philosophically unsatisfying, it doesn't predict the value of dark energy, only constrains it to a life-permitting range. Many physicists argue it may be the only explanation available if the multiverse is real. Testing multiverse theories is profoundly difficult because, by definition, we can only observe our own pocket universe. Signals from other pockets can't reach us if they're separated by eternally inflating regions. Some physicists have proposed that collisions between bubble universes might leave signatures in the cosmic microwave background's circular patterns where our bubble collided with another in the distant past. Searches for such patterns have found nothing conclusive. Others suggest we might detect the probability distribution of physical constants by studying our own universe's properties and comparing them to theoretical predictions of how constants should be distributed across the multiverse. Critics argue that multiverse theories are untestable and therefore unscientific. If we can't observe other universes or make predictions about what we should see in ours, the multiverse becomes an unfalsifiable metaphysical speculation rather than physics. Proponents counter that the multiverse is a prediction of our best theories, string theory, and eternal inflation, not an ad hoc assumption, and that dismissing it means giving up on understanding why physical constants have the values they do. Future observations and missions. The mysteries of cosmic expansion and dark energy have motivated an ambitious program of observational campaigns and space missions designed to measure the universe's properties with unprecedented precision. Over the next decade, a suite of powerful new instruments will come online, each approaching the problem from different angles and promising to either solve the Hubble tension or confirm that we need fundamentally new physics. The Vera Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, LSST, starting in 2025, with an enormous 8.4-meter mirror and a 3.2 gigapixel camera. It will photograph the entire visible sky every few nights for 10 years. This cadence allows it to discover and track millions of supernovae, asteroids, and transient events. For cosmology, LSST will measure distances to hundreds of thousands of Type Ia supernovae across the observable universe, tracing cosmic expansion history with statistical precision impossible today. It will also map weak gravitational lensing patterns caused by dark matter and dark energy shaping the growth of structure over billions of years. The European Space Agency's Euclid mission, launched in 2023, is mapping the positions and shapes of 2 billion galaxies across more than 1/3 of the sky. Euclid's observations will measure baryon acoustic oscillations and weak lensing with extraordinary precision, constraining dark energy's equation of state to better than 1%. By observing galaxies up to 10 billion light-years away, Euclid will trace how dark energy has affected cosmic expansion and structure growth over 3/4 of the universe's history. Its infrared instruments can penetrate dust to observe distant galaxies invisible to ground-based telescopes. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will complement these missions with even greater sensitivity. Roman will conduct massive surveys of supernovae and galaxies, measuring baryon acoustic oscillations and weak lensing across an area 100 times larger than Hubble could observe. Its coronagraph will also directly image exoplanets, but for cosmology, its main contribution will be precision measurements of cosmic expansion at multiple redshifts. Roman's data should definitively determine whether dark energy is truly constant or evolving over cosmic time. On the ground, the Simons Observatory in Chile is building advanced telescopes to map the cosmic microwave background with unprecedented resolution and sensitivity. These observations will refine measurements of the universe's geometry, composition, and early expansion, providing an independent check on the Hubble constant from the early universe. The next-generation CMB S4 experiment will push even further, mapping polarization patterns that reveal gravitational waves from inflation and measure the sum of neutrino masses, another cosmological puzzle. Gravitational wave astronomy will expand dramatically with upgrades to LIGO and Virgo and the construction of new detectors. The Einstein telescope, planned for Europe, will be 10 times more sensitive than current instruments, detecting neutron star mergers throughout the observable universe. With hundreds of standard siren measurements per year, Einstein telescope will measure cosmic expansion across cosmic history independent of the electromagnetic distance ladder. The Laser Interferometer Space Antenna LISA, launching in the 2030s, will detect supermassive black hole mergers, providing standard sirens across different redshift ranges and mass scales. Ground-based spectroscopic surveys will continue refining baryon acoustic oscillation measurements. The Dark Energy Spectroscopic Instrument, DESI, is measuring redshifts for 35 million galaxies, mapping cosmic structure from the present back to when the universe was less than 2 billion years old. The Subaru Prime Focus Spectrograph will conduct similar surveys in the Southern Hemisphere. These projects will measure the expansion rate at different cosmic epochs with percent-level precision, revealing whether dark energy's strength has changed over time. New theoretical work accompanies these observations. Cosmologists are developing more sophisticated models of dark energy that can be tested against upcoming data. Some explore whether dark energy could be a field that varies in space as well as time, creating regions with different expansion rates. Others investigate modified gravity theories that might explain acceleration without invoking new forms of energy. Machine learning algorithms are being trained to extract maximum information from vast datasets, finding subtle patterns invisible to traditional analysis methods. The combination of these observations should either resolve the Hubble tension or confirm it's a genuine crisis requiring new physics. If all methods converge on a single expansion rate, we'll know the discrepancy arose from systematic errors now corrected. But if high-precision measurements continue to disagree, we'll face an inescapable conclusion. The standard cosmological model is incomplete. The resolution might involve new particles, modified gravity, spatial variation in physical constants, or physics we haven't yet imagined. Either way, we stand on the threshold of a potential revolution in our understanding of the universe. What happens if we're wrong about everything? Throughout the history of science, moments of crisis when observations refuse to match theory have led to the greatest breakthroughs. The strange orbit of Mercury led Einstein to general relativity. The ultraviolet catastrophe and blackbody radiation gave birth to quantum mechanics. The discovery of cosmic acceleration might represent a similar turning point, a sign that our current framework for understanding the universe is fundamentally incomplete. If that's true, what comes next? One possibility is that space-time itself is more complex than general relativity describes. Einstein's theory treats space and time as a smooth continuum that curves in response to mass and energy. But quantum mechanics suggests space-time might have structure at the smallest scales. Perhaps it's made of discrete units, or perhaps it emerges from more fundamental entities, like quantum entanglement. Several approaches to quantum gravity, including string theory and loop quantum gravity, predict that spacetime's properties could change on cosmological scales in ways that affect expansion. Another possibility involves extra dimensions. String theory requires spacetime to have more than the 4 dimensions we experience, typically 10 or 11 total dimensions, with the extra dimensions curled up at scales too small to detect. But what if some of those dimensions are large, extending across cosmic distances but oriented in ways we don't perceive? Matter and light might be confined to our 4-dimensional surface, while gravity leaks into the extra dimensions. This could weaken gravity on large scales, producing acceleration without dark energy. Several models along these lines have been proposed, though none has yet made testable predictions that distinguish it from dark energy. Time itself might behave differently on cosmic scales. General relativity treats time as part of the space-time fabric, but some quantum gravity theories suggest time could be emergent, arising from more fundamental physics, rather than being fundamental itself. If time emerges from quantum entanglement or thermodynamic processes, its flow might vary across cosmic history in ways that affect how we interpret redshift and distance measurements. This could potentially explain why different methods yield different expansion rates. They might be measuring different aspects of how time relates to cosmic evolution. The cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales, might be wrong. Perhaps we live in an unusual region, not representative of the universe as a whole, or perhaps the universe has preferred directions or varying properties across different regions. While the cosmic microwave background's uniformity strongly suggests large-scale homogeneity, subtle anomalies in the CMB could hint at violations of the cosmological principle. If the universe is not perfectly uniform, our measurements from one location might not reveal its true nature. Dark energy itself might be a placeholder for our ignorance of how quantum field theory works in curved, expanding spacetime. Calculating the vacuum energy of quantum fields in flat spacetime is difficult. Doing so in an expanding universe is even harder. Most calculations make simplifying assumptions that might break down on cosmological scales. Perhaps dark energy isn't a mysterious new substance, but rather a correction term that emerges when quantum field theory is properly applied to an expanding universe. Working out these corrections from first principles remains one of the outstanding challenges in theoretical physics. Some theorists propose that we're misinterpreting what we observe. Cosmic expansion might not be what it seems. Perhaps redshift, the stretching of light from distant galaxies, has causes beyond simple expansion. Perhaps light loses energy traveling across cosmic distances through mechanisms we haven't identified. Or perhaps our understanding of how Type Ia supernovae work, or how Cepheid variables pulse, contains systematic errors that masquerade as dark energy. While these alternatives are considered unlikely given the multiple independent lines of evidence for acceleration, they can't be entirely ruled out without a perfect understanding of every astrophysical process involved. The most radical possibility is that the universe is fundamentally different from what any current theory describes, that we need not just modifications to existing frameworks, but entirely new concepts. Just as quantum mechanics introduced ideas completely foreign to classical physics, perhaps understanding dark energy and cosmic acceleration requires concepts we haven't yet imagined. This is simultaneously the most exciting and most humbling prospect, that despite centuries of progress, we're still missing basic truths about reality's structure, the heat, death, and beyond. If dark energy is truly Einstein's cosmological constant, never changing its strength, then the ultimate fate of the universe is sealed. Over trillions of years, cosmic expansion will continue accelerating until every galaxy beyond our local group has disappeared beyond the cosmic horizon, unreachable and invisible. What follows is a slow descent into maximum entropy, a state called heat death where nothing can ever happen again. Understanding this distant future reveals just how temporary the bright, star-filled universe we inhabit really is. The timeline begins in the relatively near future, cosmically speaking. About 100 billion years from now, the Milky Way will have merged with Andromeda and several smaller galaxies, forming a giant elliptical galaxy that astronomers have nicknamed Milkomeda. This merger will consume nearly all the gravitationally bound galaxies in our local group. The night sky from within Milkomeda will show a dense field of stars in all directions, but beyond this merged system, the sky will be completely black. Every other galaxy in the universe will have crossed the cosmic event horizon, accelerated away by dark energy to speeds faster than light can travel through expanding space. Any astronomers living in this era will face an epistemic tragedy. With no other galaxies visible, no cosmic microwave background detectable, and no evidence of cosmic expansion available, they will have no way to discover that the universe is expanding or that it had a beginning. The Big Bang will be undetectable, dark energy unmeasurable, and the true nature of the cosmos hidden forever. Their entire observable universe will consist of a single galaxy, surrounded by eternal darkness. If they develop cosmology at all, they might conclude they live in a static, eternal island of matter in infinite empty space, exactly the view many human scientists held before the 20th century. Star formation within Milkomeda will continue for a while, fueled by remaining gas and dust, but over the next few trillion years, this reservoir will be exhausted. Stars will continue forming from recycled material gas expelled by dying stars, but each generation will have less fuel available. Eventually, around 10 trillion years from now, the last stars will ignite. From that point forward, no new stars will ever form. The universe will have exhausted its ability to create luminous objects through nuclear fusion. The stars that remain will continue shining for vastly different lengths of time depending on their mass. Massive stars burn bright and die quickly, with lifetimes of mere millions of years. Sun-like stars last billions of years, but the smallest stars, red dwarfs with just a fraction of the sun's mass, burn so slowly that they can shine for trillions of years. The last red dwarf will finally exhaust its hydrogen fuel somewhere between 10 trillion and 100 trillion years from now. When it dies, the age of starlight will end. The universe will go dark except for the faint glow of cooling stellar remnants. By this point, most matter in the universe will be locked up in three types of objects: white dwarfs, neutron stars, and black holes. White dwarfs are the dense cores of dead stars like our Sun, supported against gravity by electron degeneracy pressure. Initially hot from the energy of their formation, they gradually radiate heat into space over trillions of years. Neutron stars are even denser remnants from more massive stars, packed so tightly that their matter consists primarily of neutrons. Black holes are regions where gravity has compressed matter so densely that not even light can escape. Over time, scales so long they're difficult to comprehend, these remnants will continue evolving. White dwarfs will cool to become black dwarfs cold, dark spheres of degenerate matter at the background temperature of space. This process takes longer than the current age of the universe by factors of thousands, so no black dwarfs exist yet. But given enough time, perhaps 10 to the power of 15 years, every white dwarf will complete this transformation. The universe will contain countless black dwarfs, invisible objects wandering through galaxies that no longer shine. Even these dark remnants won't be permanent. On timescales of 10 to the power of 30 years or longer, quantum tunneling allows white dwarfs to overcome the energy barriers that normally keep them stable. Atoms within them will slowly rearrange into configurations with lower energy, ultimately converting white dwarfs into spheres of pure iron, the most stable atomic nucleus. This process is so slow that it makes the current age of the universe seem like an instant, but given unlimited time, it will happen. Galaxies themselves will evaporate through a process called dynamical relaxation. When stars pass near each other, they exchange energy through gravitational interactions. Sometimes one star gains energy while another loses it. Over extremely long periods, around 10 to the power of 19 years, these random exchanges will occasionally give some stars enough energy to escape the galaxy entirely. One by one, stars and stellar remnants will be ejected into intergalactic space, leaving the galaxy's remaining mass more concentrated. This process continues until the galaxy is evaporated, with most of its stars scattered across space and the remainder collapsed into the central supermassive black hole. Black holes will be the longest-lasting structures in the universe, but even they are not eternal. Stephen Hawking showed in the 1970s that black holes emit faint thermal radiation due to quantum effects near their event horizons. This Hawking radiation carries away energy, causing black holes to very slowly evaporate. The evaporation rate is inversely proportional to the black hole's mass. Smaller black holes evaporate faster, while supermassive ones last longer. A black hole with the Sun's mass would take about 10 to the power of 67 years to evaporate completely. A supermassive black hole containing 1 billion solar masses, typical of those at galactic centers, would persist for 10 to the power of 98 years. The largest black holes formed from merging galaxy clusters might last 10 to the power of 100 years. These timescales are so vast that writing them out fully would require more digits than there are atoms in the observable universe. Yet they are finite. Eventually, even the largest black holes will evaporate in a final burst of radiation, leaving nothing behind. After the last black hole evaporates somewhere around 10 to the power of 100 years from now, the universe will enter its final state. Only a thin soup of elementary particles will remain, photons with wavelengths stretched by expansion to sizes larger than galaxies, isolated electrons and positrons separated by billions of light years, and perhaps stable products of proton decay if protons are indeed unstable. The temperature will be indistinguishably close to absolute zero. No gradients, no structure, no energy differences that could drive any process. This is heat death maximum entropy, thermal equilibrium, the end of all change. In this state, nothing happens. Nothing can happen. There's no available energy to do work, no temperature differences to exploit, no way for any organized structure to persist or arise. Even thought, if it existed, would be impossible, because thinking requires processing information, which requires energy flow from hot to cold, and no temperature differences remain. The universe won't end in drama, but in silence, darkness, and absolute stillness extending forever in all directions and for all time. Some physicists speculate about possibilities beyond heat death. Perhaps quantum fluctuations could spontaneously create new regions of false vacuum that decay into new inflationary universes, restarting cosmic evolution. Perhaps the ultimate ground state of matter is not stable, and on timescales of 10 to the power of 1,000 years or longer, all matter will eventually decay into radiation. Perhaps there are cycles we don't understand, oscillations in the vacuum energy that could reverse cosmic acceleration trillions upon trillions of years from now. These ideas are speculative, extending far beyond what physics can currently predict. For all practical purposes, in a dark energy-dominated universe, heat death is the end. The Big Rip revisited. While the cosmological constant leads to heat death over inconceivable timescales, phantom energy produces a far more violent end. If dark energy's strength increases over time, if the equation of state parameter W is less than -1, then cosmic expansion doesn't just accelerate, it superaccelerates. The expansion rate grows exponentially fast, eventually overcoming every force in nature and tearing apart every structure in the universe in a finite amount of time. This scenario is called the Big Rip, and understanding its timeline reveals just how catastrophic phantom energy would be. The exact timeline depends on how much less than the -1 the equation of state is, and how the strength of phantom energy evolves over time. Current observational constraints allow for values of W as low as -1.2, though the most likely value based on current data remains very close to -1. If W equals -1.5, well, within some theoretical models, the Big Rip would occur approximately 22 billion years from now, less than twice the current age of the universe. The destruction follows a predictable sequence determined by the strengths of different forces. Gravitational binding is the weakest force holding cosmic structures together, so it fails first. About 200 million years before the Big Rip, galaxy clusters become unbound. The expansion of space within these clusters overpowers their collective gravity, and member galaxies drift apart, each becoming isolated in an increasingly empty cosmos. Any civilizations observing this event would see neighbouring galaxies accelerate away at growing speeds, crossing the cosmic horizon and disappearing forever. 60 million years before the end, individual galaxies disintegrate. The Milky Way's spiral arms would unwind, stars scattering outward as the galaxy tears itself apart. Globular clusters orbiting in the halo would be flung into intergalactic space. The supermassive black hole at the centre would remain intact. Gravity is stronger at smaller scales, but everything around it would disperse. Any planets hosting life would see their night sky empty rapidly, stars vanishing as they're ejected from the dissolving galaxy. 3 months before the Big Rip, planetary systems become unbound. At this point, space within solar systems expands fast enough to overcome the Sun's gravity. Earth would spiral outward, along with all other planets, escaping into interstellar space. Without the Sun's heat, temperatures would plummet to just a few degrees above absolute zero within days. If any life survived this long, perhaps deep underground or in the oceans, it would face freezing darkness. But worse is coming. 30 minutes before the end, planets and stars themselves disintegrate. The expansion of space within these objects overpowers the gravity holding them together. Earth would break apart, fragmenting into boulder-sized pieces, then pebbles, then dust. The Sun would explode outward, its fusion reactions disrupted as its core was torn apart. Every planet, moon, and asteroid in the universe would share this fate, reduced to expanding clouds of debris. In the final seconds before the Big Rip, atomic bonds fail. Space expands so rapidly within molecules that chemical bonds, electromagnetic forces holding atoms together, can no longer function. Every molecule in the universe dissociates into individual atoms. Complex chemistry becomes impossible. Any remaining structures, perhaps deep in neutron stars or black holes, would finally succumb. In the very last instant, atoms themselves are destroyed. The electromagnetic force binding electrons to nuclei is overpowered by the expansion of space. Electrons are ripped away from atomic nuclei, creating a universe filled with free protons, neutrons, and electrons all separating at incomprehensible speeds. Even atomic nuclei might be torn apart if the expansion is violent enough, breaking into individual protons and neutrons. The Big Rip doesn't stop at the nuclear scale. If phantom energy continues strengthening, even quarks within protons and neutrons could be separated, and perhaps even space-time itself could be torn apart in some catastrophic quantum event that physics cannot currently describe. The universe would end not in gentle heat death, but in violent disintegration, every particle isolated from every other, unable to interact, in a state of infinite expansion rate. What makes the Big Rip particularly disturbing is its inevitability once it begins. Unlike heat death, which takes effect forever and might be prevented if dark energy changes behaviour on ultra-long timescales, the Big Rip occurs in finite time once phantom energy dominates. There's no escape, no way to prevent it, and no safe haven. Every location in the universe experiences the same fate simultaneously. The expansion of space is not something you can outrun because it happens everywhere at once. Current observations make phantom energy unlikely but not impossible. Most analyses of combined cosmological datasets find W very close to -1, consistent with a cosmological constant. The error bars typically range from about -1.05 to -0.95, making extreme phantom energy scenarios with W equals -1.5 statistically improbable. But the uncertainties are still large enough that milder phantom energy with W equals -1.05 cannot be ruled out. Such mild phantom energy would delay the Big Rip to hundreds of billions or even trillions of years from now, far beyond the heat death of individual stars but still finite. Quantum fluctuations and Boltzmann brains. In the far future dominated by dark energy, after stars have died and black holes evaporated, the universe approaches but may never quite reach perfect equilibrium. Quantum mechanics introduces fundamental randomness that persists even in near thermal equilibrium, allowing for spontaneous fluctuations that create temporary pockets of order. Understanding these fluctuations leads to one of the strangest implications of eternal cosmic expansion, the eventual formation of random conscious observers called Boltzmann brains. The concept originates with Ludwig Boltzmann, the 19th century physicist who helped establish statistical mechanics. Boltzmann realized that the second law of thermodynamics, entropy always increases, is statistical rather than absolute. In a box of gas molecules, The overwhelmingly most likely configuration is one where molecules are spread uniformly, but random molecular motion occasionally creates pockets of lower entropy purely by chance. Given enough time, even extremely unlikely low entropy configurations will occur. Boltzmann proposed a radical idea. Perhaps the entire observable universe is just such a fluctuation. Maybe the cosmos typically exists in thermal equilibrium at maximum entropy, but random fluctuations occasionally create ordered regions where stars and galaxies can form. We exist in one such fluctuation. This idea seemed to solve the puzzle of why we observe the universe in such a low entropy state, but it created a new problem. If the universe is usually in equilibrium with only occasional fluctuations, the most likely explanation for our observations is that we're in the smallest possible fluctuation consistent with those observations. Essentially, that only our immediate surroundings are real and everything else is illusion. Modern cosmology faces a similar problem in universes dominated by dark energy. If cosmic expansion continues accelerating forever, the universe approaches a state called de Sitter space, empty space with a small positive cosmological constant. De Sitter space has a temperature slightly above absolute zero due to quantum effects, similar to Hawking radiation from black holes. This temperature is extraordinarily low, about 10 to the power of negative 30 degrees Kelvin, but not quite zero. At this temperature, quantum field fluctuations continue indefinitely. Over incomprehensibly long timescales, these fluctuations can spontaneously create particles, atoms, and eventually complex structures. The probability of any particular fluctuation decreases exponentially with its size and complexity, but given infinite time, even extremely improbable events occur infinitely often. Simple fluctuations are vastly more common than complex ones. A random proton appears far more frequently than a random star, and a random star appears far more frequently than a random galaxy. This creates a troubling prediction. The most common way for conscious observers to arise in the far future is not through evolution on planets around stars formed from normal cosmic structure, but through random quantum fluctuations that briefly create brains complete with false memories. These Boltzmann brains would appear spontaneously in the vacuum, exist for a moment experiencing apparently coherent thoughts based on randomly configured neurons, then dissipate back into thermal noise. The mathematical argument is straightforward. Creating a human brain through random fluctuation requires organizing roughly 10 to the power of 27 atoms into a very specific pattern extraordinarily unlikely. Creating an entire Earth with its biosphere requires organizing perhaps 10 to the power of 50 atoms, incomparably less likely. Creating a galaxy requires 10 to the power of 68 atoms or more, even less likely still. So while all these configurations will eventually fluctuate into existence given infinite time, brains vastly outnumber planets, which vastly outnumber galaxies. If most observers in the universe are Boltzmann brains, then statistically, we should be Boltzmann brains too. But Boltzmann brains have unreliable perceptions. By definition, their memories and observations are random configurations, not accurate records of real events. If we're Boltzmann brains, we have no reason to trust our observations or scientific theories, including the cosmological theories that predicted Boltzmann brains in the first place. The reasoning becomes circular and self-defeating. This paradox suggests something is wrong with the scenario. Perhaps dark energy doesn't last forever. Perhaps the universe isn't infinite in duration or extent. Perhaps there's a mechanism that prevents quantum fluctuations from creating complex structures. Or perhaps the statistical reasoning itself breaks down when applied to infinite ensembles of observers. Several proposed resolutions exist, none entirely satisfactory. One approach argues that we should use a cosmological measure, a way of counting observers that doesn't give infinite weight to any type. Various measures have been proposed, some of which avoid the Boltzmann brain problem by weighting observers by the volume of space or time they occupy, which favours normal observers over fleeting fluctuations. But choosing the right measure requires understanding the full structure of the multiverse, which we don't. Another approach suggests that the universe isn't eternal into the future. Perhaps dark energy decays on ultra-long timescales, eventually allowing gravity to dominate again. Perhaps the vacuum is metastable and will decay to a lower energy state in the far future, ending the current phase of expansion. Perhaps quantum gravity effects become important in the far future in ways we can't currently predict. Any of these possibilities would prevent the infinite time needed for Boltzmann brains to dominate. Some physicists argue the Boltzmann brain problem indicates the current cosmological model is wrong or incomplete. If our best theories predict we should be random fluctuations rather than evolved beings, perhaps those theories miss something fundamental. This reasoning motivates searching for alternatives to eternal dark energy-dominated expansion, the impossible early galaxies. In late 2022 and throughout 2023, the James Webb Space Telescope began sending back images that stunned astronomers and challenged fundamental assumptions about cosmic history. JWST's infrared instruments can peer deeper into space and further back in time than any previous telescope, observing galaxies as they appeared less than 1 billion years after the Big Bang. What it found has created a new crisis in cosmology: galaxies that appear too massive, too mature, and too well organized to exist so early in the universe's history according to the Standard Model. The problem centers on how galaxies form and grow. In the standard cosmological picture, the early universe was remarkably smooth and uniform. The tiny density fluctuations visible in the cosmic microwave background variations of only 1 part in 100,000 provided the seeds for all future structure. Gravity amplified these fluctuations slowly over hundreds of millions of years. Dark matter clumps formed first, creating gravitational wells that attracted ordinary matter. Gas fell into these wells, cooled, and eventually collapsed to form the first stars. These stars grouped into small protogalaxies that merged over time to build larger galaxies. This hierarchical assembly process takes time, lots of time. Current models predict that truly massive galaxies containing hundreds of billions of stars shouldn't exist until the universe is several billion years old. At cosmic ages of just a few 100 million years, we should see only small, irregular protogalaxies, perhaps containing a few million to a few billion stars, still in the chaotic process of assembly. Their stars should be young and metal-poor, having formed from nearly pristine gas containing little more than hydrogen and helium. The galaxies should appear disorganized, lacking the elegant spiral arms or smooth elliptical shapes of mature systems. JWST's observations show something very different, at redshifts of 6, 7, 8 and even higher, corresponding to times when the universe was only 3 to 5% of its current age. The telescope has found galaxies that look surprisingly mature. Some appear to contain tens of billions of stars. Some show organized structures including disk-like morphologies and even hints of spiral features. Some exhibit evidence of significant heavy element enrichment, indicating multiple generations of stars have already lived and died, recycling their material back into the interstellar medium. Several galaxies observed by JWST challenged the models so severely that astronomers initially questioned whether the observations were correct. One galaxy, designated Glass, Z13, appears to have existed just 300 million years after the Big Bang, but shows spectroscopic signatures suggesting a stellar mass of several billion suns. Another, Sears 93316, appeared at first to be even more distant and massive, though subsequent analysis suggested it might be a lower redshift interloper. Still, dozens of confirmed high redshift galaxies show properties that strain theoretical predictions. The core problem is one of timescales. Building a galaxy containing billions of stars requires forming those stars from gas, which requires gas to cool and collapse from the intergalactic medium into dark matter halos, which requires those halos to assemble from smaller clumps through mergers and accretion. Each of these processes takes time. Computer simulations that include all the relevant physics, dark matter dynamics, gas cooling, star formation, supernova feedback, black hole growth consistently predict that massive galaxies cannot form as quickly as JWST observations suggest. One possible resolution involves the efficiency of star formation in the early universe. Perhaps conditions then allowed gas to convert into stars much more rapidly than occurs in nearby galaxies today. The early universe was denser, and gas clouds colliding at high speeds might have fragmented and collapsed faster. Without heavy elements to radiate energy efficiently, gas clouds might have formed more massive stars than typical today, and massive stars burn out quickly, allowing multiple stellar generations to cycle through in a short time. If star formation was 10 times more efficient in the early universe than models assumed, it could partially explain the observations. Another factor might be the nature of the first stars themselves. The first generation of stars, called Population 3, formed from completely pristine gas, no heavy elements whatsoever. Theoretical models suggest these stars might have been enormous, hundreds of times the Sun's mass, burning incredibly hot and dying in spectacular supernovae after just a few million years. If Population 3 stars were common and massive, they could have enriched the interstellar medium very rapidly, enabling subsequent generations to form faster and in greater numbers than currently modelled. Dark matter properties could also play a role. The standard assumption is that dark matter consists of cold, slow-moving particles that clump gradually under gravity. But if dark matter has slightly different properties, perhaps it's warm rather than cold, or perhaps it interacts with itself or with ordinary matter more than assumed it could affect how quickly dark matter halos form and merge. Faster halo assembly would mean galaxies could begin forming earlier and grow faster. Some researchers have proposed more radical explanations. Perhaps the initial density fluctuations from inflation were not as uniform as the cosmic microwave background suggests. If there were rare regions with significantly higher density, they could have collapsed earlier and formed galaxies faster. This would require modifying inflation models, but it might explain both the early galaxies and potentially some of the CMB anomalies. Alternatively, perhaps our distance measurements are wrong. Maybe these galaxies aren't as far away as their redshifts suggest, though this would require fundamentally rethinking how redshift relates to distance and cosmic expansion. The most troubling possibility is that the standard cosmological model's timeline is incorrect. If the universe expanded or evolved differently in its first billion years than currently assumed, the age we assign to these early galaxies might be wrong. This could happen if dark energy was stronger in the early universe, causing faster expansion and making distant objects appear older than they are. Or perhaps gravity worked differently then, allowing structure to form faster than general relativity predicts. Any such modifications would have far-reaching consequences, potentially requiring us to revise our understanding of the Big Bang itself. As more JWST data accumulates, the picture grows more complex rather than clearer. Some high redshift galaxies show exactly the properties models predict: small, irregular, metal-poor. Others defy expectations. The distribution seems broader than theoretical predictions, with both ends of the spectrum more populated than models suggest. This variety might be telling us something important about the range of conditions in the early universe, or about processes we haven't included in our models. The early galaxy problem resembles the Hubble tension in an important way. It's a discrepancy between observations and theoretical predictions that becomes more pronounced as measurements improve rather than resolving. Just as better measurements of the local expansion rate have sharpened rather than eliminated the Hubble tension, more JWST observations continue to find puzzling early galaxies rather than revealing them as misidentifications or anomalies. This persistence suggests a genuine gap in our understanding rather than a temporary observational puzzle. The crisis in structure formation, closely related to the impossible early galaxies, is a broader problem cosmologists call the structure formation crisis. Computer simulations that model how cosmic structure grows from the tiny fluctuations in the early universe to the galaxies and clusters we see today face multiple discrepancies with observations. These problems exist at various scales and epochs, suggesting our model of how gravity, dark matter, and dark energy shape the universe might be incomplete. The core of structure formation theory rests on well-understood physics. Start with the density fluctuations measured in the cosmic microwave background, about 1 part in 100,000 variations from place to place. Let these fluctuations evolve under gravity over 13.8 billion years, including the effects of dark matter, dark energy, and ordinary matter. The simulation follows billions of dark matter particles as they clump together, tracks gas as it cools and forms stars, models supernova explosions that heat and expel gas, includes black hole formation and growth, and accounts for cosmic expansion. The most sophisticated simulations, like Illustris EAGLE and Illustris TNG, include all these processes and produce universes that look remarkably like our own in many ways. But the details don't match perfectly. One long-standing issue is called the missing satellites problem. Simulations of Milky Way-sized dark matter halos predict they should contain thousands of smaller dark matter subhalos, gravitationally bound clumps that orbit within the larger halo. Each subhalo should in principle be able to host a dwarf galaxy. Yet the Milky Way has only about 60 known satellite galaxies, not thousands. Where are the missing satellites? Several solutions have been proposed. Perhaps most small dark matter halos failed to form stars because their gravity wasn't strong enough to hold onto gas when the first stars formed, and energetic radiation reionized the universe. Perhaps many tiny dwarf galaxies exist but are too faint to detect. Indeed, as surveys become more sensitive, they keep finding new ultra-faint dwarf galaxies, though still nowhere near thousands. Alternatively, perhaps dark matter physics is different from assumed. Maybe it's warm rather than cold, suppressing the formation of small halos. Or maybe the simulations overpredict small-scale structure formation for reasons we don't understand. A related issue is the too big to fail problem. Simulations predict that the largest dark matter subhalos within Milky Way mass systems should be massive and dense enough that they absolutely must have visible galaxies within them. Yet when astronomers look at the actual satellite galaxies around the Milky Way and Andromeda, they find that the largest ones, like the Large Magellanic Cloud, have significantly less mass than the theory predicts for the largest subhalos. Either the predictions are wrong, or there are massive dark matter clumps near us that have no stars, which seems unlikely. On larger scales, simulations also struggle to reproduce the detailed properties of galaxy clusters. Observed clusters often show complex internal structures, multiple peaks, asymmetric distributions, merging subclusters that simulations can produce, but the statistical properties don't always match. Some clusters appear more relaxed and spherical than simulations predict for their mass and age. Others show gas distributions that don't quite match the dark matter distribution in ways that are hard to explain. The distribution of galaxies across cosmic voids presents another puzzle. Simulations predict that voids should be nearly empty, with galaxy densities perhaps 10% of the cosmic average. Observations generally confirm this, but some studies find that the galaxies in voids have different properties than simulated void galaxies. Observed void galaxies sometimes appear bluer and more actively star-forming than expected, suggesting they're younger or have different formation histories than models predict. Perhaps the most significant discrepancy involves the amplitude of structure on intermediate scales, roughly tens of millions of light-years. Measurements of weak gravitational lensing, which probes how mass is distributed by observing subtle distortions in background galaxy images, consistently find that the universe today is slightly less clumpy than simulations predict. The parameter cosmologists use to quantify this clumpiness is called sigma-8. Cosmic microwave background observations measure the clumpiness in the early universe and predict how much growth should have occurred by now. Weak lensing observations measure actual clumpiness today. The predictions and measurements don't quite agree. Today's universe appears about 5 to 10% less structured than it should be based on early universe measurements. This sigma-8 tension is less famous than the Hubble tension, but potentially just as important. It suggests that either our understanding of the early universe is incomplete, or the physics governing structure growth, dark matter properties, dark energy effects, or gravity itself doesn't work exactly as assumed. The discrepancy could arise from systematic errors in weak lensing measurements, which are technically challenging and must account for many subtle effects. But multiple independent surveys using different analysis techniques find consistent results, making systematic errors an increasingly unlikely explanation. The growth rate of the structure also depends on dark energy and gravity. If dark energy's repulsive effect has been constant throughout cosmic history, structure should have grown at one rate. If dark energy was weaker in the past or stronger now, growth rates would differ. By measuring structure at different cosmic epochs, comparing how clumpy the universe was billions of years ago to how clumpy it is today, astronomers can test whether dark energy has evolved. So far, results are broadly consistent with constant dark energy, but the uncertainties are large, and some analyses hint at mild evolution. Modified gravity theories make specific predictions about structure growth that can differ from general relativity plus dark energy. In some modified gravity models, the enhancement of gravitational attraction on large scales that produces cosmic acceleration also affects how structure grows. These models predict different relationships between the expansion history and structure growth than standard cosmology, offering potential tests. Current data don't definitively rule out or confirm these alternatives, keeping the door open to radically different explanations. The structure formation crisis also connects to reionization, the epoch about 400 million to 1 billion years after the Big Bang, when the first stars and galaxies produced enough ultraviolet radiation to ionize all the hydrogen in the universe. Measurements of the cosmic microwave background indicate reionization occurred relatively early, but observations of distant quasars suggest it might have been more extended and complex than models predict. Reconciling these different probes of reionization requires understanding when and where the first stars formed, which depends on dark matter properties and the initial density fluctuations. One emerging concern is that simulations may be missing important physics. Current models include star formation, supernova feedback, and black hole growth, but these processes are modeled with simplified prescriptions rather than from first principles, because simulating individual stars and supernovae across entire galaxies is computationally impossible. If these approximations are wrong in systematic ways, if, for example, supernova feedback is more or less efficient than modeled, it could explain some discrepancies. But adjusting these parameters to fix one problem often makes other problems worse, suggesting the issues run deeper than calibration. The speed of gravity and cosmic expansion. One of the strangest and least discussed aspects of cosmic acceleration involves a fundamental question: how fast does gravity propagate? According to general relativity, gravitational effects changes in the curvature of space-time travel at exactly the speed of light. When a massive object accelerates, it creates ripples in space-time called gravitational waves that spread outward at light speed, just as electromagnetic waves do. This prediction has been confirmed by detecting gravitational waves from merging black holes and neutron stars. But what if gravity's speed isn't constant, or behaves differently on cosmological scales? This possibility could fundamentally alter our understanding of cosmic expansion and dark energy. The idea that gravity might not travel at light speed seems to contradict well-established physics, but on cosmic scales, we have limited direct tests. All our measurements of gravitational wave speeds come from relatively nearby events within a billion light-years or so. We've never directly measured how fast gravitational effects propagate across billions of light-years, or whether the propagation speed might change over cosmic time. General relativity assumes the speed is always exactly the speed of light everywhere, and at all times, but this is an assumption that could, in principle, be tested observationally. Some modified gravity theories predict that gravitational waves could travel at speeds slightly different from light speed. These theories introduce additional degrees of freedom beyond general relativity's single metric describing space-time curvature. In these models, gravitational effects might have multiple components that propagate at different speeds. Most such theories were severely constrained by the 2017 observation of GW 170817, a neutron star merger detected in both gravitational waves and electromagnetic radiation. The gravitational waves and gamma rays arrived at Earth within 1.7 seconds of each other after travelling 130 million light-years, proving that gravitational waves travel at the same speed as light to within 1 part in 10 to the 15th. However, this test applies only to the specific frequency and distance scale of that event. It doesn't rule out scenarios where gravity's effective speed differs on cosmological scales or at very low frequencies. Some physicists have explored whether massive gravitons, gravitational force carriers with non-zero mass, could explain cosmic acceleration. If gravitons have mass, they would travel slightly slower than light, and gravity's strength would weaken at very large distances, potentially mimicking dark energy's effects. The challenge with massive gravity theories is avoiding instabilities and contradictions. In the 1970s, physicists proved that giving the graviton mass in the simplest way leads to catastrophic problems. The theory either predicts negative energy particles that would make the vacuum unstable, or it contains mathematical inconsistencies. Recent work has found more sophisticated, massive gravity theories that avoid these problems, at least at the classical level. These theories predict that on solar system scales, gravity behaves identically to general relativity, but on cosmic scales, modifications appear that could drive acceleration without dark energy. Testing whether gravity's propagation speed varies with distance or cosmic epoch requires comparing different observational probes. One method uses the relationship between cosmic expansion and structure growth. In general relativity with dark energy, these are linked in a specific way. If you know how the expansion rate changes over time, you can predict how fast the structure should grow. Modified gravity theories often predict different relationships. By measuring both expansion history and structure growth independently, astronomers can test whether they're consistent with general relativity. Another test comes from gravitational lensing. When light from distant galaxies passes near massive clusters, gravity bends its path, creating distorted images. The amount of bending depends on the strength of gravity and subtly on how gravity propagates. In modified theories where gravity's effective speed differs from light speed, lensing effects can differ slightly from general relativity's predictions. Current observations are consistent with general relativity, but uncertainties are still large enough to allow some modified theories. Perhaps the most intriguing connection to cosmic expansion involves the cosmological constant problem. If gravity's speed isn't exactly constant but varies very slightly with the local energy density of space, this could provide a natural mechanism for why the cosmological constant is small. In such scenarios, the vacuum energy doesn't directly cause acceleration. Instead, it modifies how gravity propagates, creating effective acceleration without requiring enormous vacuum energy. These ideas are speculative and face significant theoretical challenges, but they represent attempts to solve multiple problems simultaneously. The relationship between gravity's propagation and quantum mechanics adds another layer of complexity. In quantum field theory, forces are carried by particles: photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. Gravity should be carried by gravitons, though these have never been directly detected because gravity is so weak at quantum scales. If gravitons exist and have mass, even a tiny mass of about 10 to the power of negative 32 electron volts, they would cause gravity to behave differently on cosmological scales without violating solar system tests. Detecting or constraining such small masses requires observations across vast distances. One approach uses pulsar timing arrays, networks of precisely monitored pulsars whose radio pulses act like cosmic clocks. Gravitational waves passing between Earth and these pulsars create tiny variations in the arrival times of pulses. By correlating these variations across many pulsars, astronomers can detect gravitational waves with wavelengths of light years far longer than LIGO detects. These ultra-low frequency gravitational waves could reveal whether gravity propagates at exactly light speed or differs slightly, potentially providing evidence for massive gravitons or other modifications. Another test will come from next-generation gravitational wave detectors like the Einstein telescope and LISA. These instruments will detect waves from sources billions of light-years away, allowing direct measurements of gravity's propagation speed across cosmological distances. If gravity travels even 1 part in 1 trillion slower than light at these distances, future detectors should detect it. Such a discovery would revolutionize cosmology, potentially explaining dark energy as a manifestation of modified gravitational propagation rather than mysterious vacuum energy. The possibility that gravity behaves differently on cosmic scales connects to a deeper question. Is general relativity the final theory of gravity, or merely an approximation that breaks down in extreme conditions? We know relativity breaks down at singularities inside black holes and at the Big Bang, where quantum effects become important. Perhaps it also breaks down on the largest scales, where the curvature is tiny but volumes are enormous. Just as Newtonian gravity required modification when applied to high speeds and strong fields, general relativity might require modification when applied to the entire universe. Some theoretical frameworks suggest that space-time itself might be emergent, rather than fundamental, arising from more basic quantum information or entanglement. In such scenarios, the speed of gravitational propagation could be an emergent property that varies depending on the underlying quantum state. At small scales and familiar energies, this speed happens to equal the speed of light. But at cosmological scales or very low energies approaching the vacuum energy density, the effective propagation speed might differ, producing what we interpret as dark energy. Testing these ideas requires pushing observations to their limits. Multi-messenger astronomy combining gravitational waves, electromagnetic radiation, and potentially neutrinos from the same events offers the most powerful tests. When a cosmic event produces signals in multiple channels, comparing their arrival times and properties constrains how different forces propagate. The more distant the event, the more sensitive the test becomes. An event billions of light years away where gravitational waves and light arrive even seconds apart would indicate different propagation speeds, revolutionizing our understanding. The ultimate question is whether cosmic acceleration and dark energy are telling us that space has energy, or that our theory of gravity is incomplete. These might seem like distinct possibilities, but they could be two perspectives on the same underlying physics. If gravity emerges from quantum entanglement, then changing the entanglement structure of space could both modify gravity's behavior and manifest as effective vacuum energy. The dark energy we observe might be the signature of spacetime's quantum structure asserting itself on the largest scales, a glimpse of physics beyond general relativity that we're only beginning to comprehend.